Today we're going to dive into vector addition. Um, the only thing to really note about vector addition, you do the same thing with vector addition as you would multiplication. You just um, add, if I'm adding vectors A and B, I just take each one of their components and I add them together independently, making sure I don't cross A1 to A2 or B1 to B2. As long as I keep this separation here, I'm all good. And that's the only thing really about vector addition. And this theorem that, uh, you know, A plus vector A plus vector B, um, it will just be like essentially the summation of its A1s, A2s, B1s, B2s, for however many components it has. So this can really just be, it can be X, Y, Z, uh, Q, however many coordinate directions you want, however many dimensions you want to work in, it's all possible that you would just continue to follow this. So now let's move on to some more interesting stuff. So we're back here again with vectors. And an interesting property of vectors is that they can be represented both geometrically, like when we draw them in pictures, and they can also be represented computationally and represented in the form of numbers. So that means that for every question, there's going to be two answers. And that's one of the very interesting and great properties of vectors is that they'll give you both a geometrical answer and a computational answer. Um, and both of which can help you solve your final problem. Vectors can also be moved as long as their length and direction remains unchanged. This is really important because, as we know, vectors have a direction, so we can't change their direction or you'll end up changing their sign. So what do I mean when I say I can rearrange vectors? Essentially, what I mean is that I can take a vector that looks like this. Let's call this vector E. And I can move vector E from here and I can just move it over to here. And as long as vector E remains unchanged in length and direction, I can move it wherever. I can move it all over my coordinate grid. Um, and what I say by move it, I mean I essentially picked this up and I moved it around. And as long as vector E remains unchanged in length and direction, I can do that. And that has many great benefits to me. One of its biggest benefits is I can rearrange vectors to form a parallelogram. And this is a really important idea. So these two vectors that I have here can be rearranged to look like this. And form a parallelogram. And as long as my direction and length, really want to hit this idea home, guys, direction and length remain unchanged, then I can do this. And this will end up giving me the ability to look at this hypotenuse and say, huh, this would be pretty useful if I knew that. Well, I actually have a definition of what this is. This hypotenuse will actually be equal to, so we'll call this C. C, and this is our major takeaway. C will then be equal to vector A plus vector B. So this, sorry, this is the hypotenuse of this. So let's write that out. Oops. So C, vector C, is the hypotenuse of A, B. Once there's some harpoons on there, so we know they're vectors. Okay, moving on. Multiplication by scalars. So let's take a deep dive on here. So I have vector A drawn here. This is normal vector A, unmodified by any scalar multipliers. Um, when I want to take vector A and multiply it by 2, I'm simply going to get 2 times the length that A was before. That looks about right to me. Um, and what about if I multiply A by negative? Then A will simply become the same length it was before, but it will become the negative direction. And that's all for multiplication on scalars. And so now let's take a look at that same idea I had beforehand, um, with making parallelograms. And I can look by rearranging A and considering it in a plane, I can make a parallelogram out of my vector A, specifically a parallelogram that exists in space. So let's try to draw this out. Looks something like, this is not really going to be to scale. Something, oops, maybe something like this, something like this, like that. And I do this with the components of A, or calling or moving around vector A and maybe vector B. Um, and that'll all give me this parallelogram shape. Now, this parallelogram that I drew is not necessarily consistent with vector A, but it's just to give you an idea of what that might look like on the graph. Um, so now let's move into dot product. Um, the dot product, this is not multiplication, don't get that confused. Um, but this will be, the definition of it is A1 B1 plus A2 B2 plus A3 B3 plus A4 B4, and this definition will go on to infinity, for however many components or directions you're working with. Now, here's the main question that I have. Is this quantity scalar or is it a vector? Now, the correct answer here is going to be scalar. And we'll later see an answer that results in a vector when we get to cross products. But for right now, when I'm given a dot product, I'm going to receive a scalar quantity as my answer. So now we're going to look at an example. So I have vector A, which is represented by 4, 6, and 2, and then I have vector B, which is represented by 2, 3, and 5. Let's find the cross of A, B. So the way that I'm going to solve this is I'm going to follow my definition from up here, and I'm going to take A dot B, and it's going to give me the summation. A I B I equals, so our A1 B1 would be 4 times 2 plus 6 times 3 plus 5 times 2. And if you want, you can go ahead and work that out, but that's really a good enough definition for me. So this would be our final answer. So now I'm going to come down here, um, and I'm going to look at this geometrically now. So here's my rule of dot product from beforehand. Now let's examine what this means in a geometric context. So over here, this is going to be equal to the length of A times the length of vector B, um, multiplied by the cos of theta. Now, if you want me to prove it to you, let's see what this actually means. So I already started to have some of this written out, but if I was to take the dot product of A by A, I would end up having the length of A times the length of A, and that would give me A squared. I'll just write that above. The length of A squared. What about this cos of 0? Well, if I was to draw this out, I have vector A, so this is my first A, and we'll call this my origin point. Now, if this was vector B, it might be like over here, and then I'd have some theta, but it's not. It's also A. The angle between these is 0, which is what is going to define my angle up here. So the cos of 0 we know to be 1. So that's going to give me A squared, the length of A squared specifically, times 1, which is just going to leave me with A squared. And if we look down here, oops, if we look down here, if I do the same computational approach that I took up here, it's going to end up giving me that A1 times A1 plus A2 times A2. This will go on for however many components of A I have, which will ultimately result in the length of A squared, which means that my definition shown up here will remain true, proving that A dot B will equal the length of vector A times the length of vector B multiplied by the cosine of the angle between them. And just to restate again that this cosine, specifically this theta, will be the angle of theta between these two vectors. So that's all for today.